Unmute, start video. Okay, so what shall we talk about today? Anybody have a question? I could, for example, do problems from some of the earlier chapters. Linear algebra, Fourier analysis, complex variables, differential equations, whatever. And 18. Well, what you have to do is go to, all right, let me just make sure I have things straight here. Let me go back to, see if I can go back to that. Nah, damn it. All right, I'll have to just go to the exercises again. So let me get the book out so make sure we don't have some equation number wrong. So 1018 says, look at 1063. Okay, 1063 gives us the trend, the Z component of the electric field for the TM modes. And what we're talking about here is a cylindrical waveguide. And this is the case where it's not coaxial, it's just a simple evacuated metal cylinder. And we want to find expressions for the TM folds in terms of that, TM fields in terms of that. And these TM folds, fields, then to get the rest of the fields, what you do is you go up there and solve for, let's see, let me go to that equation again. So 1063. So here's the expression for EZ, and the formulas for E rho, E phi, B rho, and B phi are given by 1060, and we're said to be transverse magnetic. That means BZ equals 0. So in other words, let me just make this clear here. BZ equals 0 in TM modes. Okay, so that's the hint, and so you don't really have very much else to do except differentiate. Let me get rid of that parenthesis, that I don't know what the hell it is, sidebar or something. Okay, what else? People can still see the screen and hear me and so forth. So let's thank you. So let's, if I don't get a question about doing a problem from back here, then I'm just going to go on to do a little more of GR. And what I was thinking of was doing a couple of examples here. Just the sphere in 3 dimensions. E super 3 means 3-dimensional Euclidean space. So this is what we're really familiar with. The 2-dimensional sphere in that is called S2. And just to make things perfectly clear for a moment, there's our sphere S2. So theta equals 0 is up here. Theta pi over 2 is there. Theta pi is down there. Phi goes around this way. Apparently, there are people who seriously believe the Earth is flat. I don't know what they think of this, the sphere. But anyway, so what are the vectors? This thing keeps going to keeps going blank on me. I've got to fix that somehow, but I'm not quite sure how. If anybody has a quick recipe for how I tell this thing not to turn off, do tell me. Let's see, QuickTime Player. See if this, no, I don't see any preferences even there, so I don't know what to do. I guess I'll just have to put up with it. So what we've got then for these vectors on the sphere is if we have a point on the sphere and which has an angle theta here. I don't know why I wrote E. All right, a vector E. If we increase theta, then the point goes like that, goes a little bit in that direction, and the vector E theta looks like that. It's a vector that's perpendicular there. Maybe I should get the sphere out here. So here's our sphere, and the vector E theta is the vector that points in the direction of those lines of longitude, or their lines of latitude. I guess they're lines of longitude. Anyway, like this. And E phi, on the other hand, is a vector that points in the direction that a point on the sphere goes when you increase phi, so it looks like that. So that's what those vectors are. And then the metric of E3 is just the metric 1, 1, 1. And so you compute the partial derivative of a point on the sphere with respect to the angle theta, and you get these this 3 vector. If you do it with respect to E phi, you get this 3 vector. You then take the dot product of those with each other, and you get a metric, which is a matrix G. I used to write that as G sub IK, but I think I'm just going to use a notation in which G means this metric with all the indices down, and G inverse is the one with the indices up. You take those inner products, what you get is this expression here. And the determinant is r to the 4th sine squared theta. The squared infinitesimal distance is then this expression here. Surprising things can happen when you change coordinates. So if you change coordinates to theta and a radius r equal to, so you're changing from theta to r, where r is the fixed diameter, the fixed radius of the sphere divided by some scale factor times sine of theta. Then what happens is your metric change, your line element changes into this, and the new metric looks like this. And the inverse of the new metric looks like that. Now, when you see this expression here, you might say, gee, that's kind of an interesting expression. And in fact, it's very close to something that one sees. So let me flash ahead to the metric that we had for that we saw in the end of the chapter on differential equations. We did a little bit of cosmology, and what are called the Friedmann-Lemaitre Robinson-Walker cosmologies. They have a metric that looks like this. The distance between infinitesimal points is dr squared over 1 minus kr squared over L squared r squared d omega squared. And this funny factor of 1 over that, this is the same factor that occurred back here. When we changed coordinates, we got this funny factor here. And this A that I put in here, this is the scale factor. And so ds squared looks like that. Okay, and those are the inverses. Now, as I said, you can imagine that we have a hyperboloid, and this hyperboloid H2 is actually pretty weird. It's a surface embedded in a semi-Euclidean spacetime. So this is a Euclidean spacetime with a metric in this case. So let me switch even colors here. So in this case, this was S2. If we're talking about, H2, the metric now is -1. So G, it's not G, sorry, let me get rid of G. It's not G, it's the internal metric. I am not quite sure what to use for that internal metric. I need a symbol, and I don't know what the hell to use as a symbol. But anyway, the metric is -1, 1, 1, whereas the metric for E3 was this metric here. What we've got here is -1, 1, 1. And the equation for a hyperboloid is r squared equals x squared minus y squared minus z squared. And the coordinate, the point P then has, geez, sorry about that. The point P has this expression here, and if you differentiate, you get these tangent vectors. If you take the inner product with regard to using this funny metric, then what you get is, for example, E theta dot E theta is this thing. And so what is that? That's r squared. And then we have a minus sign here, so minus sh squared. And then we have plus these two guys, plus, and that's just ch squared, both of theta. And ch squared minus sh squared is 1, so this is just r squared. And that's this expression here. On the other hand, if you take the dot product of these two, you just get 0. And then if you take E phi dot E phi, what you get is r squared times something else. And the something else is simply minus sh squared. So this is just minus sh squared. and minus sin squared. Let me see, do I have something funny going on here? It's sin squared, it's just sin squared with a plus sign, sorry. This minus sign threw me, but it's a dot product of this with itself. And since we have a 0 here, we can forget about the minus sign. So it's just sin squared. And so the metric G is given by this expression. Now, once again, if you screw around with your variables and change from theta to something called little r, then you get an expression like this. And this, of course, is just like the if only I could. I think I have too many chapters in this. Here we go. That's the case k equals -1. And so this is the open universe case. K equals +1 is the closed universe. And as far as we know, k is equal to 0 experimentally. So we have actually a very simple, we live in a very simple cosmology. Now it may turn out, you know, in 5 or 10 years, or sometimes in your careers, that we discover that the universe is has a k that's non-zero. By the way, the theory of inflation has become so popular that it's standard now in textbooks, whereas there's a group at Princeton that's been pushing a bouncing universe, and I think actually they're right. I was an inflation fan for 30 years or so, but I think we're going to have a paradigm shift soon. So do you want me to continue with relativity here? Let me get to maximally symmetric spaces. I'm not going to go through this in detail, but you wouldn't be surprised to hear that the sphere S2 is a maximally symmetric space. And after all, you can't get any rounder than a sphere. There are only 3 maximally symmetric spaces. One is the sphere, another is the hyperboloid that we just talked about, and the third is just simple Euclidean space. And so those are the bases of the 3 cosmologies that are the standard, as far as we can tell, the standard cosmologies. In other words, the idea here is that observation suggests the universe is homogeneous and isotropic, so it's essentially maximally symmetric in 3 space. I'm talking about space, not time, just space. And consequently, we need to, a good cosmology then would model 3-dimensional space as one of the 3, there are only 3 maximally symmetric 3 spaces. One is Euclidean space, the sphere S3 is another, and the hyperboloid H3 is a third. And these have line elements like that. So let me jump back to the sphere S3. This is a 3-dimensional sphere embedded in 4 space. And so that if this is the right cosmology, then we are actually what we think of as what looks like to us like Euclidean 3 space. At least that's what our physical space looks like at short distances. It could be, if you go to long distances, that it's the surface of a sphere in 4 dimensions. And in that case, the metric, so let me go up here and maybe switch colors again. The metric now would be simply 1, 1, 1, 1. This would be the internal metric of the 4 space. And the points in the 4 space would look like this. There's an extra angle here, sine chi, and then sine theta, cosine, then the rest of it are the normal polar coordinates. But what replaces r is L sine chi. And so then we have three basis vectors as we differentiate the point with respect to chi, theta, and phi, or phi. I don't know which is the appropriate one. And if we take the dot products of these vectors with each other, we wind up with this expression here, which is the metric that you find in it's in other words, this is the space part of the Lemaitre, Robinson, Walker, Friedman cosmologies. I've got to be able to say Friedman, Lemaitre, Robinson, Walker. I get them in alphabetical order, but it's hard for me. I choke each time. D omega squared is then d theta squared, sine squared, d v squared, and so the thing looks like this. This is exactly what one has in the, so this is the space part of the Robinson, who's the first guy? Friedman, Lemaitre, Robinson, Walker cosmology. For a closed universe, the space part is the surface of a sphere in 3 dimensions. So this is the space part of the metric. This time part we don't screw around with. And why don't we do that? Well, as far as we can tell, time is just uniform and simple. It would be amusing if that turned out to be not the case. And then life would be quite, physics would change. Interesting. By the way, as I said to you before, physics with 2 time coordinates is pretty amusing. And well, let me go on here just a little bit because we'll see what physics with a little bit of physics with 2 time coordinates. The other cosmology, the other Friedman, Lemaitre, Robinson, Walker cosmology is to say that our 3-dimensional space is really the surface of a hyperboloid H3. And in that case, the metric, instead of being this, is a metric -1, 1, 1, 1. This is just the space part of the metric. So here, let me actually do something about this. This was kind of excessive here. So let me switch back to this. So this is really, looks like that. So this is the metric for, oh, I'm sorry, what I actually need here is a minus sign. And so let me put a minus sign there. So that's the metric for the open universe, where we have we have k equal to +1. And so this is the metric in that case. You differentiate p with respect to these angles, you get these variables. And let's see, which is the easy, if we dot this with this, we're obviously going to get that. What about this top one? What is, let's see if I have the right metric. What would E chi dot E chi be with this metric? Well, then it would be L squared, and now we'd have minus cos squared, sine squared, cosine squared, plus cos squared, and then we'd have this squared plus that squared. Oh, I'm sorry, we have a whole bunch of terms. So we have cos squared of that one squared, cos squared of this one plus that one. And so that gives us, well, maybe I better do it strictly. Sine squared theta, sine squared phi, plus ch squared of cosine squared theta. So these, yeah, I guess I should have used theta and phi here also. And then the last one is plus sh squared of chi. And let's see, I just wonder, do I have the metric wrong? I should have written down what the metric was exactly, because I want this to be, this actually is supposed to be just 1. So E chi dot E chi is supposed to be just L squared. And I need one time component. It might be that it's this one with a minus sign there. Then we would have a plus sign here and a minus sign there. Then we'd combine these two into sinh squared. That would, right, and so this would be this. Okay, so the correct metric, the internal metric has a minus sign there. And I should make a note of, say, okay, so I should have done that in the text, I think. Anyway, this gives then the Robinson-Walker case, like that. And you see I've got the metric explicitly here. So anyway, there are only 3 Maximalist metric spaces, and so we use them in the 3 Friedmann, Lemaitre, Robinson-Walker cosmologies. Let's see what else I should go through. There are all sorts of things that simplify, and that are sort of complicated when they start out. You start out with them, but then they become simpler. Maybe just to amuse people here, say something about black holes here, which have become, our knowledge of them has become much greater in the last 10 years or so. Way back in the 1930s or 40s, black holes were postulated as being something that might exist, but lots of people thought, well, they couldn't exist because they were just too weird. Well, what happens is, suppose if you have an uncharged spherical elliptic star of mass m collapse within a sphere of radius RB that's less than the Schwarzschild, well, maybe I should say what the Schwarzschild radius is. All right, let's see, I've gone too fast here. So let me see, where am I? Perfect. Yeah, let's first go to Einstein's equations. Well, Einstein's equations can be derived from a very simple formula. Well, sort of simple. The simple formula is you take the metric and you allow yourself to have second order derivatives of the metric, and you want something that's a scalar, at least that's a scalar under coordinate transformations. And that scalar is called the scalar curvature. You remember that, actually, maybe I should go way back here, or I jumped ahead too fast. We talked about curvature, and the curvature is, the essential curvature tensor is something, well, one way of writing it is with all lower indices, and then it has a form that looks like this. So there you see second order derivatives of the metric tensor, and it's often written this way, where you've raised one index. Remember in GR, if you have something that is RK ILN, then what this is GK, not L, all right, let's get rid of the last one. GKS, say, R SILN, and SILN would be given by this expression here. This thing, GKILN, is the, if you take the commutator of two covariant derivatives and you look for the KI matrix element of that, that's a 4x4 matrix, you look for the KI matrix element of it, what you get is this expression here. And if you then turn this thing into a, so this is the, what are the names? I'm terrible with names. It's the, let's call it the Riemann Tensor. If you then contract it to something called RIN, which is to say RKIKN, in other words, you sum over this. When you sum over that, because you have an upper index and a lower index, that makes those a scalar. So this is just a tensor with two lower indices, a doubly covariant tensor. And if you then contract it further, say GNI RIN, then what you get is this is called the Riemann Scaler, or the curvature scalar. Anyway, this is a scalar, that's the important thing. And with that scalar, remember with the principle of least action, what do you like to have? You like to be able to say that S is equal to some scalar times, in ordinary field theory, it's just d4th x. But here in general relativity, what you want is scalar times the square root of g d4th x. The square root of g with d4th x gives you something that is invariant. And then the scale is invariant. So altogether, the action is invariant under general coordinate transformations. And this R, and so what you have then is R square root of g d4th x. G here is the absolute value of the determinant of the 4x4 matrix G. So I have sort of an abusive notation here. I guess this is why I didn't use little g in other places for the matrix. Anyway, so I'm having G stand for two different things. I also use the notation G equal GIK. And I don't know, there are only so many letters and there are so many symbols and concepts. Big G is Newton's constant. And by the way, this Einstein-Hilbert action, what does it look like actually? Well, roughly speaking, it's the Planck mass squared times R root G d4th x. And so in this Planck mass squared, this is the mass that's just absolutely enormous on the scale of elementary particles. The proton has a mass of roughly 1 GeV. The Planck mass is like 10 to the 19th GeV. And so what does this mean? This means that the tiniest change in the action makes a huge change. A tiny change in the curvature or the metric makes a huge difference in the action because it's multiplied by the square of the Planck mass. And so that means that gravitational effects are weak. That is to say, they wash out to zero if they're greater than just the tiniest amount. Anyhow, if you then apply the principle of least action to this Einstein action, that is to say, you require that zero equal the change of the action to first order, which is to say the integral, I'll just write this as g again. I'm leaving out the c squared and the 16 pi, c cubed 16 pi and so forth. You have here delta of g square root of g d4th x. This gives you the Einstein equations. And so what are these Einstein equations? These are, well, let's see. They are, for empty space, they look like this. Rik equals a half Gik R being the scalar. This thing is called the Ricci tensor. So this is empty space. And in fact, it's empty space in the absence of dark energy, dark matter, and just purely empty space. What one does to include matter and is one sets the change in the matter action as 1 over 2c, an integral of something called the energy momentum tensor, square root of g, and then the change of the metric, dik d4th x. And so then one gets the full Einstein equations, which are Rik minus a half Gik R is equal to, it turns out, 8 pi G being Newton's constant, c to the 4th Tik. So this is the energy momentum tensor. So the standard model goes in there. And this side of the equation is geometry. And this side of the equation is matter, basically. Matter, energy, etc. So let's see. I again skipped too fast. Let's go to weak gravitational field. Well, let's go first back to the equivalence principle. In fact, maybe I should have said what the equivalence principle is. It's basically that you can change to, at any given point, you can make a general coordinate transformation to a reference frame in which G is just, in which G prime is equal to eta in a small 4-volume. And in that 4-volume, you then have special relativity applying. And what we think about here is proper time, for example. This is the proper time in the coordinate system in which the speed of the particle is 0. And there you have c squared dt, dt squared, which is minus ds squared is then minus gik, all that. So in lab coordinates, it might be this, but in the coordinates of the of the particle in its rest frame, ds squared or minus ds squared is just this. And by the way, there's something called the clock hypothesis, which is interesting in that it's, I think it's kind of unexplained, which is why it's called a hypothesis. The apparent lifetime of an unstable particle is independent of the acceleration of the particle, even when the particle is subjected to high acceleration. So in fact, it's been tested in by having putting in cyclotrons or other circular accelerators, unstable particles, and then one finds that they decay at a rate that is given by this equation. It's not that they decay at the same rate as they would at rest. It's rather that they decay at a rate that depends upon their velocity in the lab frame and not and is independent of the acceleration, which is, and the acceleration is extraordinary if you have let me just switch you. If you have a particle accelerator and you've got this thing going around in a circle, and the circle might be, in the old days, the circle might have been a meter, and the particle was moving at almost the speed of light. Well, at the Large Hadron Collider, this thing is a matter of kilometers, and it's, again, moving at almost the speed of light. And in both cases, the acceleration is enormous, but the lifetime, the apparent lifetime of the particle depends only on the speed at which it's moving. That's called the clock hypothesis, and it's experimentally true. Okay, so let's see. Weak gravitation. Let me just say what the idea is. If you apply the principle of equivalence, then what you get is that, or you apply the principle of least action. In both cases, you get an equation like this: that a particle in a gravitational field follows this sort of an equation, where tau is a parameter that labels points on the trajectory, or it could be proper time. So if you go to a weak gravitational field, then you neglect the velocity compared to just the, or after all, this is the momentum divided by the mass. So this is the energy divided by the mass. And so if you neglect this compared to that, then you get this equation. And what you find eventually is you get Newton's equations for slow motion in weak static fields. You can also figure out what the time dilation is. And here we're talking about particles that are essentially at rest. So c squared d tau squared be minus ds squared to be this. And so you have this expression here. And if the particle is essentially not moving in the lab frame, then what we get is just simply this, where this thing is G00. And if we just say that G0 minus G00 is equal to this, then remember the G00 is normally negative, because the metric of flat space is minus 1, 1, 1, 1. Actually, it's minus c squared, a squared, a squared, a squared, where a is the scale factor. But the scale factor we conventionally take as unity at the present time is c squared, speed of light. Anyhow, the G00, that's this one, is negative. So what do we find? What we find is that the time the change in time is going to depend upon the position if the gravitational field depends upon position. And then if you compute the difference of the times for 2 points separated by a distance h, and you're just talking about about experiments done on the surface of the Earth, then you have the local acceleration of gravity times the height divided by c squared. Notice that this is an acceleration, or this is a squared velocity actually when you multiply. So this is a dimensionless thing. And this was measured, I think the first time it was measured was 1960, and by Pound, who was at Harvard, and a graduate student or a postdoc named Rebka. They measured the blue shift of light falling down a shaft of about 23 meters. And what they used was one of the staircases in the physics building at Harvard. So there wasn't any, it was a very cheap experiment. They just needed a laser. And, well, they used the Mossbauer effect, and they found that shift in frequencies was 2 parts in 10 to the 15th. Pound and Rebka actually died only within the last 10 years. If I'm not mistaken, Pound is somebody who did so many advanced things at such a young age. In fact, when he was young, it was the Second World War, and he did work in, I think, for the English military during the Second World War, or for the Americans, I'm not sure. Anyhow, he was promoted to full professor at Harvard without pausing to get his PhD. So he was quite a remarkable individual. I think he was the only recent case of somebody to be a Harvard physics professor without a PhD. Anyway, so let's get back to what we were talking about here. Well, gravitational waves, these, what you do is you take Einstein's equations, you linearize them, and then what you have is a wave. And these things, of course, were first discovered, or at least publicly, they were the successful detection of the merger of two black holes was announced in 2015, only 5 years ago. So you can solve Einstein's equations. Once again, Einstein's equations in empty space are just these equations. And if you solve Einstein's equations in empty space, then one of the solutions, which was found by Schwarzschild, so let me try to get to the Schwarzschild thing directly. Yeah, so Schwarzschild found this solution. So this is the line element, ds squared is, and of course, in this expression, what we're talking about here is, why don't I switch to black maybe? What we're talking about here is, of course, ds squared is equal to gik dxi dxk. And for the case in which it's diagonal, then you get, well, one solution that was found by Schwarzschild was this solution. This is for the metric. If you have a mass m and you're a distance r from the mass m, then the ds squared out here is given by this expression here, g being Newton constant, m being the mass there. And because g is so small, or because g is so small, this thing, and we're dividing by c squared, and c is so fast, this turns out to be essentially a very tiny correction in general. And the key parameter here is the Schwarzschild radius, which is twice the mass times Newton's constant divided by c squared. And for the case of the sun, this is just about 3 kilometers, whereas the sun's radius is 700,000 kilometers. So in the case of the sun, you've got this tiny Schwarzschild radius, and the sun is, well, this is obviously, if I did this to scale, you couldn't see the Schwarzschild radius. It would be too small. So for most astronomical objects that we know about, the Schwarzschild radius is much smaller than the actual radius of the object. And so Schwarzschild's solution applies out here. So the Schwarzschild solution works only out here for, if this is the radius of the sun, it's only out here that the Schwarzschild solution works. And so there's no talk of it being a black hole. On the other hand, if you do have a star or something else that collapses to a within a sphere RB that is less than the Schwarzschild radius, and I'm going to write that as RS and RH, and this is then 2mg over c squared. Then the Schwarzschild solution does apply, and then what you have is that dt is equal to d tau over square root of minus g00, and this is then d tau over square root of 1 minus 2mg over c squared r. So if you're at a point that is so let's try to see what we've got here. We've got a huge mass m inside some distance. The Schwarzschild radius here is all right. Here I'll switch to red. The Schwarzschild radius, we'll say, is out here. So this is RS. And so if you're out here, say, in fact, let me switch to green. Then if you're out here, you're kind of safe, although you're actually sort of dangerous. If you're in a very strong rocket ship, you may be okay here. But as you get close to this distance here, what happens is this thing becomes 0. And in fact, I think I should rewrite this as d tau over the square root of 1 minus r Schwarzschild over r. So if you're bigger than r Schwarzschild, you're out here, then this thing is maybe 0.99999, and dt is essentially d tau. But as you get closer, if your r is just, say, 2 times r Schwarzschild, or only a little bit bigger than r Schwarzschild, then dt, you get dt is much, much greater than d tau. So that means that a second goes by for you here, and 100 years goes by for people way out here. Okay, so, and this was something that was visibly and marvelously depicted in a movie in which some physicists participated and were allowed to participate intellectually. And the physics portrayed in the movie was pretty much correct. The only part that the director refused to listen to the physicist was that the free fall of the spaceship through I don't know if it was a wormhole or what, but anyway, that free fall, because it was a free fall, inside the spaceship, everything would have looked just like ordinary special relativity in empty space. And instead, the director insisted that it sounded like a subway train on bad tracks during rush hour. And I forget the name of the physicist. He actually won a Nobel Prize and for his work on black holes, and he's a physicist at Caltech. He gave a colloquium at UNM many years ago. God, I forget his name. I'm terrible with names. Sorry about that. So let's see. I've been going on with many different things here. I don't know if you want to hear more about such things, but so that's basically what happens. And then you see if something that takes a second, or I should say, takes a second in the local time detour, and takes 100 years or so out here for an observer far away. So the observer is way out here. Then you can imagine that if this guy sends a light signal out, the light signal has a certain frequency. By the time it gets out here, its frequency is essentially zero. And so that was the idea that that the black hole itself would be black, and that's why they were called black. Of course, I don't know, there seems to be a fascination among astronomers to call things black, maybe because they're always looking at the black sky at night. But dark matter, for example, shouldn't be dark. It should be called invisible or transparent matter. And also what Stephen Hawking pointed out back in 72 or 73, that black holes are not black. And the reason is that the gravitational field here is so strong that empty space radiates. And in fact, that radiation is such that a black hole of mass m is converted to radiation in a lifetime proportional to the cube of the mass. So if you have a small black hole, it does not last very long. And this is a very strange formula, you see, because you've got Newton's constant, and then you've got h bar, as well as c, and then mass cubed. Anyway, black holes can rotate, and in fact, most of them seem to be rotating. When they do, they drag space with them to some extent. And that's why if you look at let's see, at a black hole, maybe I should, I'll go for red so I don't encourage people to think of them as black. So you've got this spinning black hole, and the result is that the matter around it is spinning like crazy and radiating to the extent that it's so hot that it's ionized. These are then electrons and protons, and being accelerated, they radiate like crazy. And this, in fact, is, I think, what we call a quasar. Anyway, as I said, I'm terrible with names, so I don't want to go on about such things, naming them. What we have here is then the metric for a maximally symmetric three-dimensional space. It's what we've seen before. There are three kinds of maximally symmetric three-dimensional spaces: the sphere, the hyperboloid, and just ordinary Euclidean space. As far as we can tell, there's no reason to think that K is any different from zero experimentally. In any event, one can then compute Einstein's, can write down Einstein's equations and solve them for this cosmology, and then add an energy momentum tensor. The energy momentum tensor is essentially energy, mass density and pressure. So T is something like minus rho and then PPP in the very simplest case, it looks like that. And what you then have is the equations that you've seen before, namely one equation for the scale factor is A double dot over A is minus 4 pi G over 3 times rho plus 3P over C squared. That's one. And then the other equation, which is much more useful, is that A dot over A, which is what we call the square of the Hubble constant, is 8 pi G over 3 rho minus C squared K over L squared A squared. And as I said, for practical purposes, you can set this thing equal to 0 experimentally at the present time. In another 10 years, we may know that it's different from 0. Okay, now let's see. I have not seen any questions on the chat page. So I don't know, do you guys just want me to continue with GR, or would you like me to do some particular example from any of the chapters? Okay, well, having heard no objection, I guess maybe I'll go on a little bit further. So remember, the Hubble constant is A dot over A, and if you work out how pressure and pressure and mass density are related to each other, energy conservation gives you a nice equation for such things. Namely, you find that d rho dA is equal to minus 3 over A being the scale factor, rho plus P over C squared. And what you then see is that rho is some rho 0 times A0 over A times something that's we write as 3 1 plus W. And what is W? Well, W is the relation of the pressure. So if we have one object, one substance making up the mass density, then the pressure will be related to the mass density like this with some constant W. And we take that constant W and we put it here, and that gives you an expression for rho in terms of the scale factor. And the popular cases are that, my goodness, this never ends. I thought I started a new one here. All right. Anyway, what we have here is that rho is some rho 0 over A cubed if rho is due to just particles. And that's because as the universe expands with the scale factor, the particles just become farther and farther apart, and the density drops as the cube of the space the stretching of space. So this is for matter, and presumably matter, whether transparent or visible. For energy, or for radiation, on the other hand, rho sub r, well, this is rho 0 over a to the fourth, and the reason for that is that when you expand space, the wavelengths grow bigger, and therefore the energy of the photons drops proportionately. And then there's finally dark energy. Again, we see this use of the term black or dark. This is presumably just a constant. And if you expand the amount of space, it just gets bigger. And so, so that's how things go. So the total density, in other words, is the total mass density is the mass density due to dark energy, sometimes written as capital Greek lambda, being the cosmological constant. The density of matter, whether transparent or visible, and the density of radiation. And if you put those things into the Friedmann equation, in particular this equation, and in fact, if you just set k equal to 0, or, you know, the experimental value is tiny, tiny, plus or minus something that's tiny. So if you use the value that's the expected value, then which is super small, and then you can put that in there, and then you get you can integrate this equation, and what you do is you eventually get an equation that looks like this: that the time at which the universe will have expanded from scale factor 0 to scale factor A would be given by this. Now, this, of course, is assuming we have a big bang expanding from a point. And as I said, I think that what is more likely is that the universe has had a scale factor A. If this is time, then we talk about time 0 here. The scale factor A here is, well, that's A. So it was very big, it shrunk to some small number, and now it's increasing again. So this is the bouncing universe case. If we have the inflation case, then we don't say anything about prior time really, but what we have here then is something that looks like that. And actually, I didn't do that very well, so let me undo that. What we have, I guess, looks kind of like that. In other words, you have a period of inflation here, and then ordinary growth, and then you have a new kind of weaker inflation when dark energy takes over. And so the first, the total evolution over the 14 gigayears that we know about looks like this. So that's actually, I wrote a Fortran program to do this numerically, taking the Planck data as, and just doing it numerically. What I got was this, and then Z, which is, where's my formula for Z? Z is, Z is 1 over A minus 1. And so for small, in the early universe, it's just essentially 1 over A. And so Z starts out as being, let us say 10. And well, it's actually a lot more than 10. It's 10 at decoupling of photons from atoms back at around 400,000 years, but then it drops. Anyway, the scale factor in the standard inflationary picture looks like that. And for the first 100,000 years, it looks like this, and you have an era of radiation at first. And the reason for that is that rho radiation is rho radiation 0 over a to the 4th. And so for small a, you expect radiation to dominate. And that's true for about 50,000 years. And then matter starts to take over. And you see the energy, the mass density due to matter falls like this. But for radiation, it falls faster. And so the one overtakes the other at 50,000 years. And then as time goes on, in fact, here, this is the first graph gave you the picture from here to there, which is where we are now. But if you look at the future, what happens is the dark energy takes over, and this part of the curve, in this part of the curve, the radiation and matter are totally irrelevant. And you just have a dark universe expanding faster and faster. What happened before the Big Bang? Well, we don't know. Inflation is a theory that, as I said, has, I think it's in all the textbooks now, but I think it's going to be out of all the textbooks in another 10 years because it's requires these rather extraordinary assumptions, namely that we had some very tiny region of space that in which there was a quantum fluctuation of an extraordinary kind, and then given that very special fluctuation, you then have an expansion, and that expansion became the whole universe. It's, I think, much more plausible to think about bouncing solutions. If you go to YouTube and put in Paul Steinhardt and add Simons, S-I-M-O-N, apostrophe S, or just Simon. So you write Paul Steinhardt and then Simon. Simon, by the way, is somebody who was a brilliant mathematician and then used his cleverness to invest in the stock market and bonds, and became fabulously wealthy and has been supporting science in I don't know, last 20 years or so, 30. And in particular, he has the Simon Foundation, or the Simon's Foundation. And so if you go to YouTube, look for Paul Steinhardt, Simon, S-I-M-O-N, you can find some YouTube seminars by Steinhardt. I find them I find them compelling. I think that inflation is going to be rejected after a while. Okay, so we're just about out of time. I haven't heard anything from anybody asking me to do anything after problem 10.18. So I guess the only way to get a reaction out of anybody is to give another homework assignment. So I may do that. And it would be due, I guess, on the last day of class, which would normally be an exam. So what I might do is that, let me figure out when the last day of class is. But as I said, I don't know what to do if I don't get any feedback. The only thing I can think about if I don't get any feedback is to assign homework. Because when I assign homework, you then say, give us a hint on problem 39 or 42 or 16. Well, we're just about out of time, so I'm going to, I guess, say goodbye. I hope that somebody's been listening, learning something about general relativity and cosmology. Although, as I said, I would have been willing to speak about other things. And of course, there are other topics. For example, their probability and statistics. That's really important for anybody doing anything practical. Path integrals are something very interesting, and group theory is important in not only solid state physics but particle physics. And there are the way I teach group theory, I think in a painless way you learn the basic things, and then if you need to learn something that's hard, well, you'll have the background that will make that possible. All right, I'm going to quit now because we're out of time. So I'm going to stop sharing. I'm going to end for all. Goodbye, everybody.